Greetings, everybody. This is Dr. Gomez. This is another video that goes with the Chapter 9 Lecture Notes, and this is another what we call static equilibrium problem. Again, very important. And so let me go back here. So here we have, you have a, let me scroll down just a smidge here. So you have a uniform horizontal beam. You know the length L is 8 meters. And unlike the previous example, the beam itself has a weight, WB, meaning the weight of the beam. The weight of the beam is 200 newtons. Well, what that means is that the weight of the beam itself will create a torque about the pivot. So we cannot ignore that. And because the beam is uniform, we know the weight acts at the center of mass of the beam, which we know is at the exact center, at L over 2. Now there's a person who walks out on this beam, and his weight, WP, weight of the person, nothing complicated, his weight is 600 newtons, and he's at a distance D from the wall. The right end of the beam is attached to the building by this cable. The cable makes an angle of phi with the beam. That angle is given as 53 degrees. And the beam is connected to the building on the left side by this pin connection, indicated by this black dot. That, when we consider the sum of the torques, that is going to be our pivot. And the rubric for these problems is always the same. We want to find the tension in the cable, T, and we want to find the magnitude and direction of the force exerted by the wall on the beam. We mean what we call the reaction force R. I want to know its magnitude, and I want to know the angle alpha. Okay, so step one is we're going to choose the point where the beam is affixed to the wall. That is going to be our pivot. And when we take the sum of the torques equals 0, it's relative to that choice of pivot. Well, let's go ahead and let's draw all the forces acting on the beam. The beam is the object that is in equilibrium, because the various forces acting on the beam would cause it to rotate about the pivot. Okay, so I'll start at the right end of the beam. Here's the tension force T, the red, indicated by T. Remember, the tension force is always directed along the rope or cable, but away from the object. So that's T. Well, remember, if this angle is phi, if this angle in here is phi, this angle up here would be phi. So now let's break T into its x and y components. The y component of T is T sine phi, and it's positive in the positive y. The x component of T is T cosine phi, and it's in the negative x. Okay. Now let's go, now we know, what about the weight of the beam itself? Well, we know that the weight of the beam, indicated by this green vector, WB, meaning weight of the beam, well, we know it acts at the exact midpoint of the beam. Because we're unless you're told otherwise, and I don't believe that you will, these objects are uniform, so the center of mass is at the exact geometric center of the object. And remember, by definition of center of mass, any forces acting on the object act at the center of mass. So the weight of the beam acts right there. We know it is at a distance of L over 2 from the pivot. Then just moving, I'm going right to left. Now here's the person. Well, the weight of the person, WP. And then here's the reaction force. And we always draw the reaction force in Q1. We assume that the x and y components of the reaction force, we assume that they are both positive. If it turns out when we do the calculations that one of them is negative, so be it. Not a big deal. So there's the reaction force, R, the purple, and it makes an angle of alpha with the horizontal. And the reaction force has an x component we call Rx, and it has a y component, Ry. Notice Ry is in the positive y direction, Rx is in the positive x direction. So again, you got to choose your pivot. And again, your pivot in problems like this, these static equilibrium problems where some type of beam or support rod is being, is holding, in this case, it's supporting this construction worker. Well, wherever the beam or rod is attached to the wall or to the building, that is always going to be your pivot. And remember, the reaction force cannot create a torque because any force that acts at the pivot, the lever arm is 0, creates no rotation, creates no torque. All right, now remember that the conditions for static equilibrium, we always apply them in this order. We take the sum of the forces in the y direction acting on the beam, set that equal to 0. Then you take the sum of the forces in the x direction, set equal to 0. Then the sum of the torques relative to your pivot, set that equal to 0. Always do them in that order. They will give you respectively equations 1, 2, and 3. So let's look at the sum of the forces in the y direction equals 0. Well, just look at your diagram. A good diagram can save you a lot of work. T sine phi is positive. Ry is positive. WB and WP are both negative. So you have 4 forces in the y direction. T sine phi is positive. Ry is positive. The weight of the beam is negative. The weight of the person is negative. Add them up. T sine phi plus Ry minus WB minus WP equals 0. That's equation 1. Now, now let's do the sum of the forces in the x direction equals 0. Well, look at your figure. There's only 2 forces in the x direction. Rx is positive. T cosine phi is negative. Well, then they have to be equal. If they add up to 0, and one is positive and one is negative, they have to be equal. So right away, well, or we could write it like this. Excuse me, I'm getting ahead of myself. But we have Rx minus T cosine phi equals 0, which means Rx equals T cosine phi. So you can do it either way. But that's equation 2. Okay. Now let's do the sum of the torques equal to 0. We're considering the torques. We're considering this pin connection that indicated by the black dot. That's our pivot. Now remember, by definition, a counterclockwise torque is positive. A clockwise torque is negative. Let me pause this for a second. So now let's do this. We're going to obtain equation 3. We're going to do the sum of the torques. Well, we have to imagine if the beam were free to rotate about that pivot, what torque would the forces produce? Well, T would cause the beam to rotate counterclockwise. So that would be a positive torque. The 2 weights pulling down on the beam, they would cause the beam, again, relative to our choice of pivot, they would cause the beam to rotate clockwise. So the torque due to WB and WP, that's a negative torque. And remember, the reaction force creates no torque, so we don't have to worry about it. So what is torque? Well, remember, in general, torque, tau is equal to Rf sine phi. So it's force times lever arm times sine of the angle. So the torque due to the tension force, well, the force is T. It's at a distance of L from the pivot. Remember, by definition, the lever arm is the distance from where the force is being applied to the pivot. So clearly, the lever arm for the tension force is L. So we have, and it's positive, so we have TL sine phi. Now remember, let me pause this for a second again. All right, so the torque due to the tension is TL sine phi. Now notice here the lever arm is indicated. See this blue line right here. Well, notice both WB and WP, they make an angle of 90 degrees with their respective lever arms. We know that the sine of 90 is 1. So, and we know that WB and WP, they each create a negative torque. So let's do so now minus WB, and WB, the lever arm is L over 2, because we know WB acts at the exact midpoint of the beam. Then it's going to be minus WP times D. and that sum equals 0. That gives us equation 3. Now, then go backwards. Then the rubric is always solve equation 3 for the tension, then solve equation 2 for Rx, then solve equation 1 for Ry. So the algebra is very basic. I'm taking equation 3 and solving it for T, and you get this expression, WBL over 2 plus WPD all over L sine phi is equal to T. Plug in the numbers, and you get the tension, the magnitude of the tension force is 313 newtons. Now, once you know T, then we're going to equation 2. Rx is equal to T cosine phi. You get 188 newtons. Then solve equation 1 for Ry. You get this equation here. And you get 550 newtons. Now we're not quite done, because whenever a problem with the reaction force, I want to know the magnitude and the direction. And meaning I want Pythagorean theorem to get the magnitude, inverse tan to get the direction. By the direction, I mean the angle alpha. Okay, so I got Rx and Ry, 188 newtons for Rx, 550 newtons for Ry. Pythagorean theorem gives me that, and I know that R is in Q1, which I knew ahead of time, obviously, but so I know I've drawn the reaction force correctly. And then, and I get 581 for the magnitude of R. Then just do inverse tan to get alpha. Alpha is simply the arctan of Ry over Rx, and you get 71.7 degrees. And that's it. And this rubric never changed. Well, let's look at, let me pause this. I want to get a little bit of water. Let's look at one more. Okay, so let's do one more. I think you'll get the hang of it. I'm going to take one from the practice exam for exam 4. And here's the problem. We have and refer to the figure here on the right. Well, we have a uniform rectangular sign with a weight of 500 newtons. That's this ice cream shop sign. And we know that the sign is 4 meters wide, 3 meters high. So we know that it's, in other words, it's 4 by 3. And it's suspended from the support rod. And now in this case, again, the support rod has a mass, a weight of 100 newtons. And we know the length of the support rod is 6 meters. And then, so one end of the support rod is supported by, the left end of the support rod is supported by the hinge. The right end is supported by this rope. The rope makes an angle of 30 degrees with the vertical. You know, some problems, you know, it's one extra step, but we're given that this angle is 30. And we want to find, again, the rubric never changes. We want to find the tension in the cable, the tension T, and the magnitude and direction of the reaction force that the wall exerts on the support rod. Well, nothing complicated. If the angle that the rope, if the rope makes an angle of 30 degrees with the vertical, the angle theta, which we're going to use for the torque, the angle theta is 60 degrees. That's nothing complicated. And again, we're going to choose in terms of the torque where the rod is attached to the wall at this hinge. That's our pivot. Now remember, the sign is uniform, so the weight of the sign is going to act at its geometrical center. So the center of mass of the sign is located 2 meters from the right end of the rod, which places it at a distance of d equal to 4 meters from the hinge. You know, nothing complicated. Because remember, the width of the sign is 4 meters. So if the width of the sign is 4 meters, the weight of the sign acts 2 meters from the right, which makes it 4 meters from the pivot. And we'll call that, so for the sign, we're going to call that distance d. And we know the weight of the sign is 500 newtons. The weight of the support rod, WR, that's 100 newtons. L is 6 meters. That's the total length of the rod. D is 4 meters. And we know the angle theta is 60 degrees. You know, nothing complicated. Some problems will give you the angle with respect to the vertical. And again, because the sign is uniform, its weight acts at its CM. Well, it's nothing complicated. The CM is 2 meters from the right, which means it's 4 meters from the hinge, because the length of the rod is 6. Okay, now proceed as usual. Let's go ahead and take our tension force and break it into its y component, which is t sine theta. Its x component is t cosine theta. And by now you should know t cosine theta is negative, because in the negative x direction. T sine theta is in the positive y direction. Then I'm just moving to the left. Here, Ws is the weight of the sign. And notice it acts at a distance of d from the hinge. So I have Ws and d. And by now, you should know that both Ws and Wr, the weight of the sign and the weight of the rod, they both make an angle of 90 degrees with their respective lever arms. So we have Ws acting at a distance d from the pivot. Wr, that's the weight of the support rod. We know it acts at a distance of L over 2 from the pivot. And then here's our reaction force. Again, we always draw the reaction force as if it's in quadrant 1. I call the angle alpha, and we have Rx is positive, Ry is positive. Again, conditions for equilibrium. Always apply them in this order. Sum of the forces in the y direction equals 0. Well, that gives you t sine theta plus Ry minus Ws minus Wr equals 0. That gives you equation 1. Sum of the forces in the x direction equals 0. Rx minus t cosine theta equals 0. Or Rx equals t cosine theta. It's equation 2. Third condition for equilibrium, the sum of the torques equals 0. And we're using this hinge as our pivot. And again, the reaction force creates no torque because it acts at the rotation axis. It acts at the pivot. Well, again, by now, hopefully you know the torque due to the tension force is positive. The torques due to Ws and Wr are negative. So the tension force, let me pause this. Okay, so the torque due to the tension force is positive. Well, again, it's force times lever arm times sine of the angle. So it's T, L. Remember, L is the length of the rod, so the tension force acts at a distance of L from the pivot. So it's TL sine theta. Then minus the weight of the sign times D. So minus Ws times D. We know the angle is 90 degrees. Then minus Wr, the weight of the support rod, Wr, times L over 2. And that sum equals 0. Then now solve equation 3 for T. Solve equation 2 for Rx. Solve equation 1 for Ry. That never changes. Well, so doing the algebra, T is equal to the following expression. I'm just algebraically solving equation 3 for T. And you get this expression here. And when you plug in the given numbers, we know everything. We know D. We know D, L, theta, and I know Ws and Wr. So plugging in all the values, you get T is 443 newtons. So again, solve 3 for T, then just go backwards, solve 2 for Rx. Well, Rx is T cosine theta, 222 newtons. Then solve equation 1 for Ry. You get Ry is equal to this expression. Plug in the numbers, you get 216 newtons. So we're pretty much done. Magnitude of R, Pythagorean theorem, as you get 310 newtons. To get it, the direction, meaning we want the angle alpha, inverse tan. So you get Pythagorean theorem gives you the magnitude of R is 310 newtons. Arctan gives you alpha is 44.2 degrees. And that's it. So the rubric never changes. And a good diagram like the one here can save you a lot of, can really help you out a lot. Let me go ahead and save this video and get it posted.